In the previous videos this week, we've seen this very useful function map that works on lists. So it takes any function which takes A's to B's, and then it takes a list of A's to a list of B's, applying this function to every single element of the input list to generate the output list. Now, map is actually a very useful pattern for almost any kind of other data structure. So here's a quick example I'm going to show you first. So let's say we have a data type of trees. So we have a tree with A's in, which is either a leaf or it's a node with a left subtree, some data, and a right subtree. And now we can write a function that looks very similar to map, but for trees. It's going to take a function which takes A's to B's, and then take a tree full of A's to a tree full of B's. So let's see how to write this. So we're going to take the function f and the tree, and when the tree is a leaf, then it becomes a leaf. And when the tree is a node with a left subtree and a piece of A data and a right subtree, then we're going to make a new node, map the tree at the left, apply f to the thing in the middle, and map the tree to the right. So you can see this is quite similar to how it worked for lists. The empty list went to the empty list, and a cons went to a cons. But now we're doing a leaf is going to a leaf, excuse me, and a node is going to a node, and we recursively do the substructures, so the sublist or the tail of the list in the list case, and the subtrees here, so the left subtree and the right subtree, and we apply the function f to the data in the middle. So let's see how this works on an example. So if we do map tree and take a tree full of strings and work out their length, so we're going to map the length function over a tree full of strings, and let's say we've got a tree with hello world in it, then it's going to take each of the strings in this and return something with exactly the same structure as the original tree, but each of the strings will be replaced by its length, like this. So they're both 5 in this case. So what's the general form of map then? We can think of many other kinds of data structures. And in general, we're going to have a function which is map x for that kind of data structure, which takes a function that takes A's to B's, and then takes xa to xb. So we've seen examples where x was list and tree, and now we're going to look at a few more examples of this very useful kind of pattern. Now the thing to keep in mind with map is that not all definitions of this type are going to make sense, and we'll see at the end of the video some rules for determining which of them make sense. But a general thing to keep in mind is that this map only works on the things which are contained within data structure. So it should preserve the shape of the data structure. And we'll see how this works with a few examples. So the first one I'm going to show you is maybe. So if we could think of a list as a container which stores a bunch of elements in sequence, and we can think of a tree as a kind of container which stores elements in a tree shape, then we can think of maybe as a container which either stores 0 elements or 1 element. And then using this idea, we can say we can map a maybe by saying we take the container which has 0 elements, that's nothing, and produces nothing. So we have map maybe function f nothing equals nothing. And we have map maybe just a is going to be just f of a. And now this has the same type as the other map functions for lists and trees that we've seen so far. It takes maybe a to maybe b. So if we've got something which generates maybe a results, and we've got a way of turning a's into b's, then we can get something that generates maybe b results. So let's see how this works. So again, we can do map maybe of length. If we give it nothing, then we get nothing. If we give it just hello, then we get just 5. And notice here the same idea, that we preserve the shape of the input. So if the shape was nothing, we get nothing. If the shape was just something, then we get just something. It's only the data contained within the container that changes. For a slightly more complex example, we can use higher order functions. So if we think that a tree is something which has a shape which is tree shaped, and a list is something which has a shape which is list shaped, Then we can think of this other kind of weird container with string a. What is this? Well, a value of with string a is a function from strings to a's. And we can think of this as a container that for every string contains a value. So it may have infinitely many different values in it, one for every string. So for example, we could have something which is the container which only contains booleans for strings which are greater than length 5. So for example, we could have well, let's say it's a container that for every string contains its length. So let's call it lengths with string int, and this is going to be muck with string, takes input string and returns its length. And then we can ask what is the value of this string within this container. So value of, so we're given a string and a with string a, then we get an a. So to work out the value of it, we take the input string, the match on make with string, this is some function f, and return f of s. So this is an example of representing a container using a higher order function, except now the container is infinitely wide in the sense that for every string it has a value, and in this case its value is its length. So now if we reload, then we can say what's the value of hello in the lengths container? Well, it's 5. Now, being a container, with string has a map function. So if we have a container of a's, so that's one a for every string, and we have a way of transferring a's to b's, then we get a b for every string. So let's see how this works. So we've got an f that takes us from a's to b's, and we've got a muck with string, and it's got a function in it which we're going to call g here. And now we have to return a with string. So we're going to use the constructor make with string. So now the question is what goes here. So it has to be a function. So a good guess is to say it's going to be a lambda, which is going to take an s. And now what? Now, for working out this kind of problem, it's always a good idea to write out the types. So for instance, we know that f goes from a to b, and we know that g goes from strings to a's, because the g came from this with string a argument, and with string is defined to be from strings to a's. Now what we need to generate is something which takes strings and returns b's. So we can see how to do this by fitting together these two functions. We've got a function that goes from a to b, and we've got a function that goes from strings to a's. So one thing to do, if we've got a string, we apply g to it to get an a, and then we apply f to the result to get a b. So we're going to have this kind of answer. So then let's try loading this in to see if it works. Seems to. Now let's say we had this value of hello, and with lengths it just told us the length of hello, but we might be interested in whether or not the length is greater than 5. So we could do map with string, take a length, if length is greater than 5, return true, otherwise return false, to lengths. So we have a way of adjusting this container. We can adjust the results. And then it's false, because hello is exactly 5, not greater than 5. But if we type in hello world, then we'll get true. So map with string gives us a way of adjusting the values inside the container for every string. Now, if you think back to the previous video on composition, you can see this is an example of composition here. We've got f applied to g applied to some value. So one way of rewriting this is just to say it's f applied to g. And this accurately captures the idea of plugging the result of g into f. And that's really what's going on here. Now, it may seem that we could always define map for any data type which has one type argument like this. But here's an example where we can't. So the fun data type here is the type of functions which go from that data type, to itself. So for instance, the type fun int is all the functions which go from ints to ints. So we can type So one example of a value would be muckfun negate. You can see that takes for any number type, it's a function on itself. Now, can we read this as a container in the same way we did for strings? Well, let's try writing a map function. So we've got a function f that takes a's to b's, and we're going to have a function here, again g, which is going to take a's to a's. So now what we've got is a function which takes a's to b's, a function g which takes a's to a's, and what we want over here, so we've got to produce a fun, so I'll just call it muckfun, and now here we've got to produce something which takes b's to b's. So now we can't plug things together like we could before. So we've got an f which takes in a's to b's, and we've got something that takes in a's and gives us a's. I want something that takes in a b, but we've got nothing to put the b into here. There's no functions that accept a b. So really, the only function we can think of which takes b's to b's with no other information is the identity function that we saw in the last video. So this type checks, but is it the right answer? It feels a little bit weird because we're not using g. So let's try and come up with some rules for what map ought to do in order to be a sensible function. So what makes a good map? So one thing to do is to think about the idea of preserving shapes. And if we're preserving shapes, then it should be the case that if we apply map to the identity function, then we should get back what we started with. Because intuitively, that means we do nothing to the values. I mean, if we won't do anything to the shapes anyway, then it should stay the same as well. So it should be the case that for any map x function that we write, if we call it with the identity, then and any value, then that should be get back to here. So that's true, for instance, for map maybe. So if we call it with the identity on nothing, then we get back nothing. And if we call it with the identity on just x, then we'll get back just the identity applied to x, and that's the same thing as just x. And if you do a proof by induction, then you can see that for trees and lists, this is also the same. Now let's try it for our definition of map fun. So map fun for the identity applied to muckfun g is muckfun the identity. So this putative definition of map fun applied to identity does not preserve the value we started with. So it's completely changed it, in fact. It's changed it from being some function g to being the identity function. So this means that we can sort of disregard map fun as a good definition of map. Another useful property of map is the preservation of composition of functions. So this is the idea that if we have map x f, and we compose that with map x g, so remember this is really the same thing as for every value x is, we're doing g first to every element, preserving the shape, and we're doing f to every element after that, preserving the shape. Point is that this should be the same thing as map x f composed with g on the value x. So this is sometimes called a fusion rule. What's happening is we're taking these two loops here, these two maps, and we're saying take x, do g to every element, and then do f to every element. And this one is saying take x, and then do f then g to every element. So this is a good property of maps, and it can also be a good way of optimizing a program, because in some sense we've changed what was two loops before and fused them into one loop, like this. So in summary, we can define map for any kind of container-like data type. So the examples I've shown you are lists and trees and maybe, and functions that go from some fixed type, so x here, to values a. And non-examples of maps and non-examples of container types are self-functions, functions that go from a to itself. And the way we can split these two examples is by checking that the map obeys what we've called, what are actually called the functor laws. So these are laws for being a functor. And in a later week, we'll come back to defining functor as a standalone concept. But for now, we can think of functor as anything which has a map-like function.